In section 10.4, we're going to highlight some of the basics of conic sections. Most likely you have done this before in other classes, but conic sections get used quite a bit here in chapter 10, so we cover them again. And I like to cover section 4 first before we go into the other sections, because we need some of these fundamentals here, and at least need to review them because they're going to come up in the first few sections of chapter 10. So there are 4 basic conic sections that we're going to talk about, and the reason that they are called conic sections is because you can create them by cutting a cone into sections. So if you look at a cone and you cut it a few different ways, depending on how you cut it, you will get the different conic sections. So if we slice this cone perfectly horizontal, the shape it's going to make is a circle. If we slice it at an angle, but the angle is not large enough that it still cuts through both sides, it's going to make an ellipse. So it's still going to be a closed figure like a circle, but it's not going to be the same radius horizontally and vertically. So it might be stretched out in one direction or the other. And then just so this thing doesn't get too crowded, I'm going to draw the other 2 on a different conic section, on a different cone. So now if we cut this thing again at an angle, but this time it's much more of a pronounced angle, so that we don't cut through both sides, what we're going to get is a parabola. And then the last one, if we cut it perfectly vertically, you'll see that we get 2 shapes. And it looks like 2 parabolas, one of them opening up on the top, and then the other one opening down on the bottom. And that's called a hyperbola. So these are the 4 conic sections that we are going to be talking about. And we're going to start with the circle, because that one is probably most familiar to you, and we will go from there. And give me just a second. There we go. Let's get some more room here. So the basic format for a circle is x minus h squared plus y minus k squared equals r squared. And the hk is the center of the circle, and r is the radius. So we could graph these just by plotting the point HK, and then from HK, in the XY plane, it's easiest to just go up and down from there, our units. So go left and right R, go up and down R, and you can get 4 points on the edge and then connect them with a circle. So we're going to find the equation and sketch the graph. Of the circle centered at -1, 3 with a radius of 2. So we're given the h, the k, and the r, and we just have to remember the formula. So the formula is x minus h squared plus y minus k squared equals r squared. Now don't ever get rid of the x and the y. Those are variables. What we're getting rid of is the h, the k, and the r. Those have specific values based on this particular circle. So we're given the h, the k, and the r. So we can plug them in and clean it up a little bit based on what they look like. We're going to have x minus -1 squared plus y minus 3 squared equals 2 squared. And there's two things here that we should clean up. That minus -1 can be written easier, and the 2 squared we can rewrite. You should never FOIL this, though. You should go ahead and leave it. This is considered graphing form because we can very easily see where the center is and what the radius is. If we FOIL it out, it's not as easy to tell. So this would be better to write as x plus 1 squared plus y minus 3 squared equals 4. That would be our equation for our circle. And then to graph it, we're going to plot the center. We said the center is at -1, 3. And then we have a radius of 2. So from that point, we can go up 2, we can go down 2, we can go left 2, and we can go right 2. The radius is the distance from the center to the edge in any direction. So there's our point, -1, 3. And we went 2 units in every direction. And that would be our circle. So most likely you have dealt with circles before, so we're not going to spend too much time on circles. But the other ones might not be as familiar to you, so we're going to spend a little bit more time on those. So we're going to jump to ellipses, and those are very similar to circles. There is just one major difference. And you'll even see in the formula what this difference is. We still have the x minus h squared and the y minus k squared. The difference is, though, instead of having it equal to a common radius squared, we have it equal to 1. And the reason for that is because we're going a different distance in the x direction and the y direction. So there's not a common radius horizontally and vertically. So I can't just multiply through by one number that cancels out both denominators and moves it over to the right-hand side. So instead, what we do with ellipses is those radii for each of the individual directions stays with their variable. So HK is still the center. The A value is how far we move horizontally from the center. And I know it's the horizontal distance because it's the value that's under my x, and x is the horizontal axis. And then that would make B my vertical distance from the center, because B is under the y. So those are the basics that we need to know about the equation for an ellipse. Depending on which one is larger, the A or the B, one of these is going to be called our major axis and one's going to be called the minor axis. So let's just suppose that A is greater than B. That means that this ellipse is going to be longer than it is tall. We're moving farther horizontally than we are vertically. That means the horizontal axis is our major axis. So the length of the major axis would be the total distance from one side of the ellipse to the other. Well, A is just the distance from the center to the edge. So the length of the major axis would be 2A. And the length of our minor axis is 2B. If the B was larger, then we would just flip-flop those. So whichever one is bigger is considered the major axis, and whichever one is smaller is considered the minor axis. So we want to identify the center. The length of the major and minor axes, and sketch a graph. For x minus 2 squared over 9 plus y plus 1 squared over 4 equals 1. So this is an equation for an ellipse because I have two different denominators. If they were the same denominator, then I could just multiply it over to the other side and it would look like the equation for a circle. And I would be going the same amount of radius in every single direction. But because they are different denominators, that tells me I'm going a different distance horizontally than I am vertically. And that's what makes this an ellipse. So we identify our center the same way we do with a circle. So this is x minus h squared, y minus k squared. So the formula has subtraction in it. So when we pull those numbers out for hk, we pull them out opposite from what we see. So even though we see x minus 2, we pull out a positive 2 because the formula has subtraction in it. And when we see y plus 1, we're going to pull out a negative 1 because the formula has subtraction. The only way our subtraction could have turned into addition is if we were subtracting a negative. So this is our center. This ellipse is centered at 2, negative 1. And because the 9 is larger than the 4, our major axis is going to be our horizontal axis. And then our vertical axis will be our minor axis. So remember, this denominator in the formula is a squared. So a squared is 9. That means a is 3. So when we draw this, we're going to be moving horizontal 3 units. B squared is 4. That means b is 2. We're going to be moving vertically 2 units. So that's just another confirmation that we're moving farther horizontally than we are vertically. This is our major axis. And the length is from one side of our ellipse all the way to the other side. So we have to double this a value, because the a value is just the distance from the center to the edge. So major axis length is going to be 6. Minor axis length is going to be 4. And with that information, we can sketch our graph. So we've got to plot the center at 2, -1. Horizontally, we can move 3 units in each direction. Three units left and right. And then vertically, we move 2 units up and down. So we've got our point 2, -1 here. And we're going left and right 3 units, up and down 2 units. So we can see this thing's a little bit wider than it is tall. And that's what makes it just a little bit different than a circle. Now we're going to move on because our last two I think are the most difficult. They're going to take the longest. Parabolas, again, you most likely saw in algebra class, but in algebra we only look at parabolas that are open vertically. And we could technically open a parabola horizontally. And you may have not seen that before, because in algebra we only deal with functions. And a parabola that opens horizontally is not a function, so we don't really address that in algebra class. So we could have a parabola that opens up or down. And the formula, the basic formula, is just going to be y equals a times x minus h squared plus k. HK is the vertex of the parabola. And then the a value tells us whether it opens up or down. If the a is negative, it's going to open down. If a is positive, it's going to open up. We could also determine the a if we knew the vertex and we knew one other point on the graph, and we'll do an example of that. So this much, at least so far, you may remember from algebra class, but we could also have parabolas that open left and right, and their formulas are similar, but we switch all of the x and y parts. So when a parabola opens vertically, it's solved for the vertical variable, which is y. When it opens horizontally, it's going to be solved for the horizontal variable, which is x. So we're going to have x equals a times y minus k squared plus h. Notice my h and my k switch spots as well. That's because k is the y component of the vertex, so k has to stay with your y. So it's still true that hk is the vertex. And if A is positive, this thing is going to open to the right. If A is negative, it's going to open to the left. So whatever variable our parabola is solved for, that's going to be its orientation. So if it's solved for y, or if y is the linear variable, it's going to be a vertical parabola. If it's solved for x, or if x is the linear variable, it's going to be a horizontal parabola. Now, there are some other very specific details we could get into. They're not real important to what we need to cover here in Chapter 10. A parabola has something called a focus and a directrix and things like that. Just like with ellipses, ellipses have foci, and we're not really going to be concerned with that for what we need to do here in this chapter. Mostly we just need to be able to identify what these shapes are, what direction they open in, how to write the equations, things like that. We're going to find the equation of a parabola that opens vertically upward. It has a vertex at 2, 5, and it passes through the point (412). So the parabola opens vertically and it opens upward. So we have already an idea of what this parabola is going to look like. It's going to be one of these, which means I know the basic formula is going to be y equals a times x minus h squared plus k. We were also given the vertex, so I know the h and the k. So I can plug those in. So now y equals a times x minus 2 squared plus 5. The fact that this thing passes through the point 412, that's just one of many points that this parabola is going to pass through. We could use that information to help us solve for a. So we can plug that in for x and y. And then the only thing that we won't know in that formula that we have is the a. So we can plug the 4 in for x and the 12 in for y and use that to help us solve for the a value. Because this equation is not going to be done until we know a. So typically we would not plug in anything for x and y. Those are variables. But we're going to do it just for a second, just so we can solve for a. So 12 is equal to a times 4 minus 2 squared plus 5. I know that that combination of x and y should work on this parabola. And that's enough information for us to figure out what a is. And now we can solve for a, because a is the only unknown there. So we'll subtract over the 5. And when we do that, and we'll go ahead and figure out this number. 4 minus 2 is 2. And then when we square that, we get 4. And we'll get 7 equals 4a. and we could divide the 4 over, we get a is 7/4. So the only way that this parabola could possibly have a vertex at 2, 5 and pass through the point 4, 12 is if a is 7/4, which means the equation for this parabola must be y equals 7/4 x minus 2 squared plus 5. So let's look at one more example. This time, let's find the equation of the parabola. With vertex at the origin, symmetric with respect to the x-axis, that passes through the point three, 1. We want the equation of the parabola with vertex at the origin. It's got to be symmetric with respect to the x-axis, and it passes through the point 3, 1. So if the vertex is at the origin, that means the vertex, that means HK is 0, 0. It is symmetric with respect to the x-axis. So let's go back and look at what our options were. Symmetric with respect to the x-axis. The x-axis is the horizontal axis. So if it is symmetric with respect to the horizontal axis, it's got to be one of these horizontal parabolas. The vertical parabolas could be symmetric with respect to the y-axis, but this one is going to be oriented horizontally since it's symmetric with respect to the x-axis. Now we don't know if it opens left or right, and that's okay. That's all. We'll figure that out once it goes. Once we figure out the a value. But actually, if we look at this point that it goes through, if it's got a vertex at 0, 0 and it goes through 3, 1, you can kind of sketch this thing already and have an idea. If it goes through 0, 0, it's got a vertex at 0, 0 and it goes through 3, 1, and it's got to be symmetric with respect to the x-axis. That means it also has to go through 3, negative 1. It's got to look like that. So our basic setup for these horizontal parabolas, whatever direction it opened, that's what it was going to be equal to. So this is going to be equal to x, and we have x equals a times, remember y and k stick together because k is a y value, y minus k squared plus h. We know that hk is 0, 0, so that's going to simplify this thing down to x equals a y squared, because the k zeroes out and the h zeroes out. And now we can use that 3, 1 point to plug in for x and y so that we can solve for the a. So when x is 3, y is 1. So when x is 3 from that point, y is 1. Well, 1 squared is 1, and then a times 1 is just a. This means that a has to equal 3. And we get the equation x equals 3y squared. And notice that we got a positive value back for A, which confirms what we got on our drawing, that A had to be positive because it was opening to the right. The last conic section can be the most difficult, and it's the hyperbola. It definitely has the most components to it, and it can be the trickiest to draw. Just like our parabola, there are two options for how a hyperbola can be drawn. It can open vertically or it can open horizontally. The formula looks very similar to that of an ellipse. There's one major difference. So as I write this, see if you can spot the difference between the equation of an ellipse and the equation of a hyperbola. The major difference is right here. With an ellipse, we had addition between our two terms. For a hyperbola, we've got subtraction. Everything else about this formula is exactly the same. So this is just one option here. Because I have my x term first and my x term is positive, this hyperbola is going to open horizontally. Remember, a hyperbola has two pieces to it. It's kind of like two parabolas that open away from each other. So I'm going to have one parabola opening in the negative x direction and one opening in the positive x direction. If I switch those two guys and have the y written first, everything about it stays the same, except I'm going to write the y term first and the x term second behind the subtraction. Now my y term is positive. That means this is going to open vertically. So one piece is going to open up, the other piece is going to open down. So here, it's going to look like this. And then this one will have one up and one down. The HK is not actually a point on the graph. The HK is a point exactly halfway in between those two pieces of our graph. So the HK is like the center. It's not the vertex or anything like that. It's more like what we call it in the ellipse and the circle. HK is not part of the circle or the ellipse graph either. So it serves more the same purpose there. Now drawing these things, I'm going to focus just on one or the other because drawing these things can be kind of tricky. The A and the B serve a very similar purpose as they do in the ellipse. So let's just look at x minus h squared over a squared minus y minus k squared over b squared equals 1. So we know this one's going to open horizontally. HK is the center. A is the horizontal distance. And y is the vertical distance. Or excuse me, B is the vertical distance. When we put all of that together, and I'm not going to draw axes since I don't actually have point values here. So here's my HK. from this point, I can go horizontally A to the right and to the left. I can go vertically B up and down. Now, with an ellipse, we would plot a point and connect them. But with a hyperbola, what we do is we create a box. And through this box, we draw diagonals for asymptotes. Since we already said ours is going to open horizontally, the left and right edges of this box are going to be points on our hyperbolas. And we call those vertices. And our hyperbola is going to follow those asymptotes in and touch the vertice and then follow it back out. And then the same thing on the other side. Follow it in, touch the vertex, follow it back out. If we switched our two terms around so that the y term was first and the x term was second, everything would have been drawn exactly the same, except the vertices would be up at the b's, and we would have drawn those pieces opening up and down instead. And I want to show that one as well, and then we'll do an example. So if we had y minus k squared over b squared minus x minus h squared over a squared equals 1. So this one opens vertically because the y is first, the y is positive. Everything else about this is the same. HK is the center. A is your horizontal distance because it's under your x. B is your vertical distance. And we use this information to draw a box, and then we draw the diagonals of the box. The only thing different is where we are going to draw our actual final pieces of our hyperbola. So if we plot our HK, and from there we go horizontally A units left and right, vertically B units up and down. We use that information to draw a box, and then the diagonals of the box. The only thing different is we said this one's going to open vertically. So now my vertices are at the top and the bottom when I moved B units away from HK, and I'm going to follow my asymptotes in to that point at the top and the bottom. And that would be my hyperbola. All of the preliminary work is exactly the same. Plotting the center, going out A units horizontally, B units vertically, the box, the asymptotes, everything's the same. The only difference is where we draw the actual pieces of the hyperbola. Sometimes we draw them on the left and right, and that's when your x term is positive. Sometimes we draw them at the top and bottom, and that's when your y term is positive. And now here, these would be considered our vertices. So let's look at a quick example. Let's sketch a graph of x minus 1 squared over 9 minus y plus 3 squared over 16 equals 1. And identify the vertices. So we need to know first that this is a hyperbola. And it's a hyperbola, it's the only one where both terms are squared and there's subtraction in between. It looks just like an ellipse. The only difference with an ellipse is there's addition in between. So subtraction means hyperbola. The term that's positive tells us which direction it's going to open in. So because our x term is positive, it's going to open horizontally. The center is your HK, and remember our formula has subtraction in it. So when I pull out those numbers in the parentheses, I'm going to pull out their opposites. So even though it says minus 1, I pull out positive 1. And it says plus 3, I'm going to pull out minus 3. So this hyperbola is centered at 1, negative 3. A squared is 9, which means A is 3. My horizontal distance is 3. B squared is 16, which means B is 4. So my vertical distance from the center is 4. That's everything we need to graph this. So I'm going to plot my center at 1, negative 3. From that point, I'm going to go left and right 3 units. I'm going to go up and down 4 units. And we make a box with those points. And then we draw diagonals through that box. None of this so far is actually part of our hyperbola graph. This is all just preliminary work so that we can draw an accurate hyperbola graph. Now the very last step goes back to the fact that this thing opens horizontally. So now I'm going to draw the pieces of my hyperbola on the left and the right hand sides of this box, which makes these 2 points my vertices. And I'm going to follow my asymptotes in on the left and right to draw my hyperbola. So we need to know what these points are. I was at 1, negative 3, and those points are the horizontal points. Remember, our horizontal distance was 3. So I was at 1, negative 3, and I did horizontally 3 units left and right. Now if you drew this nice and accurately, you could just pick them off the graph. But from 1, negative 3, if I go left 3 units, that's going to subtract 3 from my x-coordinate. That should be at negative 2, negative 3, and you can confirm it from your graph. It is at negative 2, negative 3. And then from 1, negative 3, if I move right 3 units, it's going to add 3 units to my x-coordinate. I'm going to be at 4, negative 3. So my y hasn't changed because I haven't moved up or down any. I'm just moving left and right from my center. So these are my vertices. Your vertices are left and right from your center because our hyperbola opens left and right. If this opened up and down, then our vertices would be up and down from our center, and we would use the b value to find them. Now the very last example I want to do has to do with tangent slopes. So we have to remember from Calculus 1, tangent slope is derivative. It's dy dx. So we did a lot of those basic problems back in Calculus 1, but now that we know a couple of new graphs, I want to do a tangent line to one of these new conic sections. And we're going to do some more of these in later sections with some different methods, but this one we're going to do with the Calculus 1 method, which is implicit differentiation. So we are going to find the equation of the tangent line, to the graph, and we're going to do a sideways parabola because that one is probably new. You may have done to a regular parabola or any other just regular old function back in Calc 1, but most likely you didn't do anything that was really a non-function in Calculus 1. So let's say x squared equals negative 4y squared. And we need a point, so let's say at the point, oh, I'm sorry. If we want this to be a parabola, we want a sideways parabola, we want x to be linear. So we're going to say at the point negative 4, 1. So a tangent line, a basic equation for a line is y equals mx plus b. That's what we want our final answer to look like. For the m is slope, remember. And we want this particularly to be a tangent slope, not a secant slope or any other type of slope. And if we want it to be a tangent slope, that means we need to use derivative, dy dx. So we're going to go into this equation and differentiate everything with respect to x. And this is going to be considered an implicit derivative because this function is not solved for its output variable of y. Or it's not even a function, actually. So the derivative of x with respect to x is just 1. When we do the derivative for y, it's going to be considered a chain rule. So start off with normal derivative. We're going to do the power rule. The old power comes out front, so we have negative 4 times 2 is negative 8. And we rewrite our base, and we subtract 1 for the new power. But then we also have to multiply by dy dx. Technically, y is a function of x. We just don't know what it looks like, because y is not solved for x. So if we clean this up a little bit, we've got 1 is equal to negative 8y dy dx. And we can solve this for dy dx, because dy dx is where we get tangent slope. So to solve for dy dx, we've got to divide the negative 8y over to the other side. So we get negative 1 over 8y. That's how we get tangent slope. This will give us tangent slope anywhere on our parabola. All we need to know is the y-coordinate. And we know the y-coordinate. They gave us a specific point to do this at, negative 4, 1, but it says that tangent slope is dependent upon the y-coordinate. So all we need is the 1. So at negative 4, 1, dy dx is equal to negative 1/8. So slope is negative 1/8. So now we've got a point and we've got a slope, and we can use that information to set up the equation for a line. So we can plug this in for x, this in for y, this in for m, and solve for the b. So 1 is equal to negative 1/8 times negative 4 plus b. So 1 is equal to a half plus b, which means b is a half. So you get y equals negative 1/8 x plus a half. And just for fun, I wonder if we could graph this. I have never tried to graph sideways parabolas on Desmos before, but let's see if we can do it. So we've got x equals, we said negative 4y squared. Nice. Excellent. So it does it. And then we said our tangent line was y equals negative 1/8 x plus 1/2. Perfect. And look at this. If we zoom in, there's our point, negative 4, 1, right there. And we can see that our blue tangent line is beautifully, perfectly tangent to our sideways parabola, which is the red graph. The only issue right now is the only way we know how to do this derivative is with implicit differentiation from Calc 1. So this is, I guess, a little foreshadowing to something that we're going to see here in our other sections of Chapter 10. We will learn a different way how to do this derivative besides that Calculus 1 method. But it still does work. The old tried and true method from Calculus 1 still works.